Okay, now let's consider a couple of questions, perhaps the area of this region corresponding to this picture. I've got a new picture here. Or even if we've got some function f of xy, then of course, since x is in this direction, y is in this direction, we could have a z-axis coming out of the board and have a graph of some function f of xy, and we might want to find the volume of the graph, and I said area, but it would be the volume under the graph of f of xy corresponding to this region, within this region. So let me change that area to volume. Okay, to answer either question, what we need to do is something that should be familiar to you from first year calculus, the idea of partitioning an interval, because that's how you develop an integral. Okay, so I say it should be, and I don't necessarily assume that it is. So what we do is a partition of the interval from 0 to 2, from y equals 0 to 2, is just 0 equals y1, which is less than or equal to, that's not less than or equal, it's less than y2, less than, and so forth, less than some arbitrary index, y sub I for some arbitrary index I, and then that's less than y sub n, which equals 2. That's what we mean by a partition of the interval from y equals 0 to y equals 2. Now, usually we're going to either use a uniform interval so that y2 minus y1 is the same as y3 minus y2, etc. So each interval has the same width, or at least we're going to limit the maximum length of an interval in the partition in order to set up an integral, again, in a way that should be at least, should at least jog your memory of something that you did in first year calculus. Okay, well then we want to partition for each, okay, for each y, let's just say that here is, you know, we've got a bunch of y values, okay. So here's y sub n, and of course here is y sub 1, or maybe we call that y sub 0. So we have n intervals, and actually it's probably better to call that y sub 0, so let's make that 1 into a 0. Okay, now we're going to partition the x, okay? And what we're going to look at is a partition of a given yi interval. So, okay, here's y sub I, and over here is a value of x, which is the square root of y sub I. So what we want to do is understand that our interval corresponding to y sub I goes from 0, x equals 0, to x equals the square root of y sub I. So the interval I want to partition is x going from 0 to the square root of y sub I. That's going to correspond to this interval, or to this part of the region under the graph. So I'm going to use green to indicate that, and I'm going to say, okay, let's see, the interval goes from 0 up to what? So, well, 0 is going to be our first value of x, and that's going to be less than x1, less than x2, etc. and we'll have some value of x, which I'll call x sub j, just some, again, for some arbitrary index. And that's going to go how far? That's going to go up to y sub I. So our last value of x I'm going to call x sub m, so we don't have to have the same number of intervals in our x partition as we do in our y partition. So we're going to call this number of intervals in this partition is going to be m. The number of intervals in this partition is going to be n. Okay, and the last number in the partition, of course, is going to be our final value of x, which is the square root of y sub I. Now, and kind of pay careful attention here. Okay, between y sub I and y sub I plus 1, now let's go between y sub I minus 1 and y sub I. That would be like maybe between here and here. Here's our y sub I, here's our y sub I minus 1. We take this x partition, okay, well, between y sub I minus 1 and y sub I, we've got an interval from here to here. And that interval has been partitioned like so. So now what we've done with these two partitions is we've divided this strip up into little rectangles. Now if x sub j is here, let's say that's x sub j, then the interval from x sub j minus 1 to x sub j, where x sub j minus 1 would be here, would correspond to this little region of the graph. Okay, well, that little region, let's sketch it a little bigger over here. Okay, at this end, x equals xj minus 1. Over here, x equals x sub j. Here, y equals y sub I minus 1. Y equals y sub I. The area of this region is just going to be x sub j minus x sub j minus 1. So let me pick a good color for the area. It's xj minus 1 times yi minus yi minus 1. And I'll just call those dimensions delta xj times delta yi. That's the area of the region. Now, if I want to get the total area under the curve, I just add up all the areas of these regions. And we're going to do that. We're going to form a Riemann sum and just see how we would possibly do that using a sum and approaching an integral and see what integral we get out of this.